orbit will have a g of 9.73 meter per second square. That is the variation due to the latitude we call. Okay. Next, we're going to learn Kepler's laws. Let's take a look at what is Kepler's law. Kepler has 3 laws. Kepler's first law says that all planets move in elliptical orbits with the sun at one focus. So see, look at the orbit. It is so-called elliptical and with sun at one focus. Kepler's second law says the radius vector r drawn from the sun to a planet, which is right here, that's a planet of m of p, sweeps out equal areas. When the planet moves, that vector r will sweep out the area, let's call dA, will sweep out equal area in equal time intervals. What does that mean? For example, if we consider a dt time interval, and when the planet has a large r, and it will sweep out a skinny area of dA. Now imagine if our planet is right here and with a relatively small r, for the same time interval of dt, it has to sweep out the same amount of area, so therefore we have to get a slice of area of equal to that slim one. So for the same dt time, the planet actually moves smaller angle compared to a planet when it is closer to the sun. It has to move through a larger angle. And we know that can be expressed by angular velocity omega. That is the angle turned over the time. So for the same time dt, if the angle d theta is larger, then you have a larger angular velocity. So we say that when the planet is relatively away from the sun, it has a smaller angular velocity. When the planet is close to the sun, it has a very large angular velocity. So that is the second law of Kepler. It says the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. Kepler's third law says the square of the orbital period of any planet is proportional to the cube of the semi-major axis of elliptic orbit. Now, semi-major axis, let's look at this elliptical orbit. Well, any elliptical orbit should have 2 focus, F1, F2, and this direction, little a defined as semi-major, little b defined as semi-minor. And the relationship between A, B, and C, what is C? C is the distance from one focus to the center of this orbit. That is C. The relationship between A, B, C is a squared plus b squared equals to c squared. And this C has special meaning. We define C over A as eccentricity. Now imagine if F1, F2 both focus move to the center. When F2 approach to here, isn't that C equal to 0? So when 2 focus goes to the center of the orbit become 1, and we have a circular orbit. So a circular orbit C equals to 0. Therefore, the eccentricity for circular orbit equals to 0. So if you have a larger eccentricity, which means that the orbit is very much elongated, like the orbit of Pluto, it's very much elongated. That makes that sometimes Pluto is even closer compared to Neptune, because when the orbit is very much elongated, it has a chance getting very close to the sun. Okay. Now I'm going to prove Kepler's second law. Kepler's second law we just learned that the radius vector drawn from the sun to a planet sweep out a area. We name it dA. in the time of dt. So if the planet moves as velocity v, and v time dt give us the distance it travels, and the area of this triangle dA equals to 1/2 base time the height. Because it's very small, you can view this as triangle. The height is the vector r. And on the other hand, that the force between the sun and planet is that of gravitational force Fg. It is gravitational attraction force. According to the definition of a torque defined as the force cross the lever arm. So in this case, our lever arm is that vector r. Obviously, it has a 180 degrees angle with respect to the attractive force Fg. So when the lever arm has a 180 degrees angle with the force, then r cross F is Rf sine 180. That equals to 0. Therefore, in this case, that torque caused by gravitational force equals to 0. We learned from previous chapter that when a torque equals 0, then since this is the only torque on the planet, and then sigma torque also equals to 0. On the other hand, sigma torque equals to d angular momentum over dt, the rate of change of angular momentum. When the rate of change of angular momentum equal to 0, the angular momentum is constant. L is a constant. Well, L defined as r cross p. R is this position vector r. And p is the linear momentum of our planet. That is the mass of planet times its linear instantaneous velocity v. So our angular momentum equals to r cross this linear momentum mpv. Now, since we already know that dA equals 1/2 of base time height. So if we continue on that, we have that dA equals to, now we can replace that our R and V. You see this R, you see this V? Because in our case, R and MP, as a matter of fact, this is the tangential velocity. So when we have a vector cross another vector, that is this vector magnitude times that times sine of the angle between them. Right now, radius and tangential is 90 degrees. Sine 90 is equal to 1. So the angular momentum, as a matter of fact, is mass of the planet and R, the magnitude, and R times V. So we have this dA can be expressed as, since dA is 1/2 of that R V dt, if we move this R in, and we can replace by the magnitude of the angular momentum, and we get that L over 2 MP and dt. So what's replaced is actually this and that, because dt is still here and the 1/2 is still here. So we replace this R and V, that equals the magnitude of angular moment divided by mass of planet. That is this pair we replaced. Okay, so let's take a look. Now, if we differentiate this area with dt, this dt will be gone. So we have that L over twice of mass of planet. Now, since we already reached the conclusion that angular momentum is a constant because the total torque on the planet is equal to 0. So if this is a constant, mass of planet is constant, then the rate of dA dt is a constant. So this is the so-called Kepler's second law that says that the radius vector drawn from the sun to a planet sweep out an area in the equal areas in equal time interval, which means dA dt is constant. Equal area, equal time intervals. That is Kepler's second law. Now let's take a look at Kepler's third law. Kepler's third law says the square of the orbital period of any planet is proportional to the cube of semi-major axis of elliptical orbit. Now imagine that this is a planet, mass MP, this is the mass of the sun, and this is the radius. Well, if the orbit is elliptical, and we can replace this r by the semi-major little a. So I'm going to prove this by using a circular orbit. So first of all, we learned that sun will attract the planet with a gravitational force F of g. Fg equals to capital G, mass of the sun, mass of the planet, divided by the separation square. Since this is, let's assume this is a circular orbit, then that equals that planet does circular motion, so that equals mass of the planet times its centripetal acceleration, and centripetal acceleration is v squared over r. This v is the tangential speed of circular motion. So we can easily get this v equals to 2 pi r divided by the period. So if we look at this equation, that mass of planet simply cancels. We have capital G, mass of the sun, over r squared equals to, on the other side is v squared over r. V can be replaced by 2 pi r divided by period. V is squared right here because centripetal acceleration is v squared over r, and divided by this little r. As you can see, one of r cancels, but here is r squared. If we combine everything, the result comes out as t squared over r cubed equals to 4 pi squared divided by capital G, mass of the sun. So this is the so-called the square of orbital period of any planet is proportional to the cube. If you move this one to here, then it's proportional because this is a constant. So we can express in this way. T squared equals to a constant k times the orbital radius to the cube. And if it's elliptical orbit, we can replace this little r by a of the cube. This k is a constant. Now if we just calculate the k for the solar system, which is the planet rotate around the sun, then we're plugging the mass of the sun here. And we do have this table list all 9 planets rotate around the sun, and give us this constant k very close to that 2.9 of 10 to negative 19. That is on page 399 of your textbook, the table 13.2. Now let's use this Kepler's third law, which this is third law, to calculate something. There's a so-called geosynchronized orbit. What is it? Well, imagine this is a top view from the North Pole, and Earth rotates from west to east and rotate like that. And this is the North Pole. Okay, well, there's a city on the surface of the Earth, so it is how far away from the center of the Earth? That's 1 RE. Now imagine we have a satellite, a certain height above the surface of the Earth. What we want is when the city finish one rotation, that takes 24 hours, 1 day, that satellite also finish that one complete rotation, which means the satellite is always above that particular city. So we can send signal to the satellite. This satellite can relay to another satellite, so we can send our signal to another city, which is maybe on the other side of the Earth. This is so-called the geosynchronous orbit. How far exactly this orbit above the surface of the Earth? Well, the height is relatively close to 6 of RE. I'm going to prove that. So let's start from here. This is a circular orbit because the satellite rotates about the center of the Earth. Now, if we want the satellite to finish one rotation in one day, just as the Earth finished one rotation in one day, so period is 1 day, that is 86,400 seconds. Now, we're going to find out what is the separation R between the satellite and center of the Earth, since this is the orbital radius. And again, this is satellite rotate around the Earth, so this is mass of the Earth. Right now, if we are interested in this R, so we need to place everything else on the other side. So 4 pi square of G, mass of the Earth, and okay, if we do this, it's the other way around. Okay, let's say that should be the other way around. Okay, let's say that we are interested in R, so this goes here, and then we have this G M E T square on the numerator and the 4 pi square on the denominator. If we plug in the right number for capital G, mass of the Earth, be careful T, you cannot plug in 1 day because everything must be in SI unit. So SI unit for G, 6.67 times 10 to negative 11. Mass of the Earth, 5.98 times 10 to the 24 kilogram. T, right here, you have to plug in that 8.64 times 10 to the 4 of second because that's SI unit. Don't forget about square. And then 4 pi square. And you can get this R cube. Later you do the cube root, and you will find that actually the R comes out as 4.2, very close to 4.2, times 10 to the 7 of meter. Well, compared to the radius of the Earth, that is 6.4 times 10 to the 6 of meter. So isn't that true? The ratio is close to 7. And if capital R is 7, which is from the center of the Earth to the orbit, if this is 7 of RE, isn't that true? After we subtract 1 RE, the height will become 6 RE. This is how high the satellite has to be in order to be in the geosynchronous orbit.